Good day, grade 12. Welcome to my YouTube channel. Today we're going to look at the calculation in chemical equilibrium, but now we're given the Kc, which is the equilibrium constant, but now we're going to find the initials. Now we're going to do the reverse method. Now let's look at this. It says during an industrial preparation of ammonia, nitrogen gas and hydrogen gas react in a closed container until the following equilibrium is established at constant temperature of 472 degrees Celsius. Kc, which is the equilibrium constant, is 0.1 at this temperature. The volume of the container is that. Very important. We're given the Kc and the volume of the container, and the volume of the container is dm3. Now, if you're looking at this equation, it's a nitrogen and hydrogen produces the ammonia, and then we're given the heat of reaction there. It's negative 9.2 kilojoules, and this simply means that our forward reaction, the forward reaction is what? Is exo, because we're given the negative there. And then our reverse, that means it's what? It's endo, right? That's very important. Now we're told at equilibrium the concentrations are, right? We're given the concentration of ammonia at equilibrium is that, and the concentration of hydrogen at equilibrium is that. Now the question, it says calculate the initial mass of nitrogen gas. The initial mass. If you remember, we were always given the initials, and then we'll just use the initials and find the concentration at equilibrium using the table. But now we're going to work backwards, right? We're going to use, we're given the concentration at equilibrium. That means they're at the bottom of the table, the last column or the last row in the table. So we're given that. Now we wanted the initials, what we always given. So now that we are given Kc, we're going to use that Kc. Kc is what? At 0.1 we're given, and then we're given the Kc, and there's concentration at equilibrium. So what are we going to do now? I'm going to use the Kc expression. Kc is equal to concentration of product, which is the product, it's ammonia. There's 2 there, and there's 2 there in front, and then over concentration of what? Reactants, it's nitrogen times the hydrogen, that's to the power 3, right? From there, equation that we're given, and then now that I have the Kc and the concentration of the hydrogen and ammonia, I will get the concentration of ammonia, of nitrogen at equilibrium. So substitute the Kc there, and the concentration of ammonia, that's 2.7 times 10 to the power negative 3, and then there's 2 there, so it will be 2 over the concentration of nitrogen is the one that we want at equilibrium. So the hydrogen, it's 1,221 times 10 to the power negative 1 cube. And then if we do the math there, so we're going to have the concentration of nitrogen, it's going to be 2,71 times 10 to the power negative 3 all to the power 2 divided by 0.1 times by 1.22 times 10 to the power 2 to 1 to the power negative 1 cube. And then the answer there for that, if you punch that in the calculator, it will be 0.04 mole per dm3. This is the concentration of nitrogen at equilibrium. We were given the concentration of ammonia and the concentration of hydrogen, which are these, but we're looking for this at equilibrium, right? We got the concentration of equilibrium. That means we can go back to our table, to the traditional way, and substitute there. The nitrogen that we just got, it's 0.04, and then the hydrogen is 1,221 times 10 to the power negative 1, and the ammonia, it's 2.7 times 10 to the power negative 3, right? Now, having the table, we're working backwards. Now we have the concentration here, but we wanted the number of moles at equilibrium. So what we're going to do, we're going to take this value and multiply by the volume, which is this volume. So we're going to say this value multiplied by 0.5, we get the answer there. So if we multiply this value by 0.5, which is the volume, it's going to be 0.02, and then this value we multiply by 0.02. We're using the formula that says N is equal to CV. So we wanted the number of moles. This is the concentration. These are the concentration. The concentration multiplied by the volume, and then we'll get that. So if we're here, we multiply by volume, we'll have 0.06, and then here we'll have when we times, it's going to be 1.35 times 10 to the power negative 3. And we know this amount here, this number of moles at equilibrium is the same number of moles here. So we'll put that value there again, 0.35 times 10 to the power negative 3, and then it will be 0 there, right? The question here, it says the initial mass, it says calculate the initial mass of nitrogen gas. So what we want is this, right? So if we have, remember, this is 2x, remember this is 2x. So if 2x is equal to that, so this will be x, and this will be 3x, right? And then this will be 2x, and then 2x is equal to that. So I'll divide this by 2. So if I divide this by 2, I'll get an x. So my x here, I hope that makes sense, guys. Since there's 1 here, it's going to be 1x, and since there's 3, it's going to be 3x. Since there's 2, it's going to be 2x. But now 2x is equal to this, so I'll divide this by 2 to get an x. So if I divide that by 2, so I'll get the value that is 6.75 times 10 to the power negative 4. So this is x and this is 3x. So this I'll multiply by 3 because this is x and then this is 3x that I want. So I'll say this x multiplied by 3 and I'll get that. So if I multiply that by 3, it's going to be 2,025 times 10 to the power negative 3, right? Then the value that we want is this one, right? So normally what we do, we used to say this amount minus this amount in the reactants. This amount minus this amount is equal to that. So we'll say that amount is x. So we'll say x minus 0.75 times 10 to the power negative 4 is equal to 0.02. Again, this amount minus this is equal to that. Here is it. So I'll transpose this to this side. I'll add. So my x will be 2.07 times 10 to the power negative 2 mole. This is the initial in mole, but they wanted the mass. They wanted the mass, so we're going to change and say number of moles is equal to mass over molar mass. And then we take that 0.7 times 10 to the power negative 2. And then we want the mass, and then the molar mass of nitrogen. Remember, this is nitrogen that is needed here. So the molar mass of nitrogen is going to be 14 times 2, which is 28. And then we cross multiply. The mass of nitrogen, it's going to be, if you punch that in the calculator, it's going to be 0.58 gram. It's the mass of nitrogen, which is the initial. Even at this number of moles is what? Is initial. I hope that makes sense, guys. Cheers. Bye.